Okay, we should start. Reminders and announcements about things, hopefully, that you're already familiar with. Um, Homework 2 has been graded. You should be able to see your grades on Gradescope and also on Canvas. If you have any questions or if you have any regrade requests, please use Gradescope. Homework 3 is due tomorrow. This is entirely on Canvas. It's all multiple choice. You get 2 attempts at it. It's very much like your homework 0. And really, it's meant to be a part of your midterm preparation. In the sense that to kind of go through homework 3, you need to be, you'll have to cover everything that we've seen in the semester so far. So it can help you. And speaking of midterm, there's the midterm on class next Thursday right here. Please show up on time. It will cover everything that we've seen till last Thursday. Any questions about these three things? Yes.
So when it comes to the exams, what topics will be covered?
Everything that we did in class and of course homeworks till last Thursday. I sent out a review document that actually lists out the topics. Yes. Obviously not. We have not covered it. Yes. We'll be talking about boosting and ensembles and SVM and logistic regression and neural networks for the rest of the semester after the break. Other questions? Yes. You would not need it. I'll provide scrap paper. You really don't need anything other than sufficient number of writing instruments. Preferably pens because they are harder to erase. But other than that, you don't need anything. You wouldn't need your notes. You should not be using your notes or your calculator, or who uses calculator? Your phones or laptops or such things. Yeah. You cannot use a, you will not need a calculator. Yeah. I don't like doing calculations, so I'm not going to inflict that on you. Yes.
Did Jeremy memorize this already, but is it just multiple choice, free response, multiple choice?
Combination of that. Yeah. Why do people ask that? Usually, I've never had that question before. This semester, I've had it 3 times. I'm curious, does it change how you think about it? It does? Afterwards, you can tell me offline why. Other questions? So my plan for today, mostly to kind of a review of what we saw so far. And I have some amount of canned material that I can go through, but really I'm hoping that you'll be asking questions. We can do that as I go through the review, or if you have any specific topics that you would like to revisit or specific questions, we can do that also. That was the plan. Oh, there's a question on, yes. There's a question on this thing. Can we review mistake bound learning and extending it to the perceptron algorithm? I'll do that. But I did want to kind of, there's a tiny bit of computational learning theory left over from the last lecture. I wanted to get that done. It's literally just like a overview of computational learning theory and where it sits in modern machine learning. I do want to mention that before we jump into the review. Okay, so that's the plan for today. Anything else you want to throw on the agenda? No. Okay. So in the last lecture, we looked at VC dimension, and I'm not going to revisit the definition right now. And I introduced VC dimension as a sort of a counting trick. Given a set of given a classifier, a hypothesis space, you can ask whether a certain number of points can be shattered or not. And I kind of hinted that VC dimension is useful because it allows us to think about Occam's razor and agnostic learning and these sorts of ideas, but for infinite hypothesis spaces. And the reason it's relevant is because VC dimension behaves like log of the size of the hypothesis space. Essentially, to show that a hypothesis space which has infinite number of functions in it is learnable in the pack model, you basically need to say that the VC dimension is polynomial, at most polynomial, in the dimensionality. So for instance, with we saw this thing where with d-dimensional linear classifiers, the VC dimension is order of d. Because it's linear, which is a polynomial, linear classifiers are learnable in the pack model, and so on. More specifically, I just wanted to introduce a couple of expressions. So remember we saw the setting of consistent learners, where if you have a classifier that, if you have a hypothesis space that you can always find a consistent classifier with any data set, then we had this bound that said 1 over epsilon log size of h plus log 1 over delta. If you have more than these many examples with which your classifier is consistent, then it generalizes with low, with high probability, with low, it will have low error in the future. The equivalent expression with VC dimensions is this thing here. I will never, in good faith, expect you to memorize that. But notice that it has a 1 over epsilon. There is something like a 1 over delta. It's a 2 over delta, but that's just a constant. And then there's another 1 over epsilon here. Let's ignore that for now. But notice that instead of log size of h, there is a VC dimension. So once again, like a VC dimension behaves like log size of h. If the VC dimension is a polynomial in the dimensionality, then a consistent learner will have the pack bound. This is for a consistent learner. You can also think of the same thing for an agnostic setting. The agnostic thing, oh my God, this is so, typing this up was a pain. In the agnostic setting, if you have m examples with probability at least 1 minus delta, so with probability more than 1 minus delta, the generalization error is going to be less than the training error plus this expression here. Which means the training error, if the generalization error, if your training error is small and this quantity is also small, then your generalization error will also be small. And look at the other quantity that needs to be small. It's something involving the VC dimension. If it's a polynomial, if the VC dimension is polynomial in the dimensionality, then hopefully this is not too big. Yes. VC is Vapnik-Chernon-Menkes. This is the thing that we covered. I mentioned it only once because I have a hard time pronouncing the name. So I will pull up the relevant Vapnik-Chernon-Menkes, Chernon-Menkes. It's just a name. The name of the two people. Vapnik was, both of them were Soviet mathematicians. Vladimir Vapnik, I think he's still alive and he probably works for Meta now. Or he is affiliated with Meta. So basically the idea is that if your VC dimension is small, then learning can be, learning has the potential to be successful. But what is the meaning of VC dimension being small? It's just saying that your classifiers cannot fit too many data sets. Your classifiers are not very expressive. The set of functions you're learning is not so expressive that it can even express the noise in the data. That's the intuition here. I don't want to spend more time on this, given that we are, I promised the day for review. What the kinds of things that you should be familiar with here is, we should be able to compute the VC dimension for different kinds of functions. There will be a homework, not this homework, but there will be a homework after the break, where I will be asking you to compute VC dimension for different classes of functions, possibly including this one, axis parallel rectangles and so on. Okay, let's step back up a bit. Let's go back to the broader context of this unit. We're talking about computational learning theory. So you need to know what's pack learning, the definition that led to the whole field here. And the most important point here is not just for pack learning, but also for machine learning, is we care about generalization error. We really don't care about training error, because it might be possible to make the training error arbitrarily small if you just memorize the entire data. But we care about performance on future examples. And in this context, we looked at two kinds of functions, either finite hypothesis spaces or infinite hypothesis spaces. In the finite setting, we derived, in some amount of detail, a connection between the size of the hypothesis and the sample complexity. If you have a certain number of examples, and that number is at least more than some function of the size of the log of the size of the hypothesis space, then with high probability, your generalization error will be low. In other words, we'll have pack guarantees. You should be able to derive and understand these sample complexity bounds. And the game here really boils down to computing the size of the hypothesis space, counting the number of functions. So if I tell you the name of a certain type of functions, you should be able to count how many functions there are. And typically this involves the kind of puzzles that you might see in like a combinatorics class or permutations and such things. That's for the finite hypothesis class. But with infinite hypothesis classes, the idea of counting the number of functions does not make any sense because it's all infinite. But there are some infinite sets of functions that are more or less expressive than some other infinite sets of functions. So in that context, we need to revisit this question of how do we compute sample complexity? And the answer is VC dimension. We define shattering and VC dimension. And I walked through a few examples, I think 3 at least examples of how to compute the VC dimension for 3 function classes. The intuition is that the VC dimension behaves like a measure of complexity for a function class. Higher VC dimension implies more complex functions, implies more sample complexity. Specifically, what that means is if you use a function class that's more has a higher VC dimension, then to be able to prove that the pack guarantee exists, you need more examples. Higher VC dimension does not guarantee that learning will fail. It just means that with higher VC dimension, to prove pack guarantees, you need more number of examples. There's a subtle difference here. In more generally, with computational learning theory, we looked at pack learning, and pack is a fairly general definition, but the whole thing is based on an assumption that your instances are drawn from a fixed and possibly unknown distribution over the instance space. The fact that it is fixed is extremely important because that's what allows us to derive all the bounds that we did. In practice, that's a very strong assumption. If you think of a distribution over the instance space, the kinds of things that people write about in an email in 2025 might be very different from the kinds of things people write about in an email in 1995. Clearly, over time, the distribution over the space of all emails has changed. So what can we say from that? Does this mean that every classifier that's trained on 1995 data is guaranteed to fail in 2025? Not quite. What it really means is that we have no guarantees. There's no guarantee of success. It does not guarantee failure, but there's no guarantee of success either. But with this assumption, we looked at this idea of Occam's razor. Occam's razor is this idea that if you have a more complex set of hypotheses, then in order to be able to prove anything, you need more examples. And we looked at that in multiple different, in all these four criteria. Consistent learner is one where no matter what your data set is, your learner will find a classifier that perfectly agrees with the data set. And with the and in the variant of not the variant, the thing that you can change with a consistent learner, if you want to remove the consistency requirement, you land yourself in the agnostic setting, where there's no guarantee that the classifier that your learner produces is consistent with the training set. These are the two possible cases. Either your classifier always produces something that's consistent with the training set, or you have no such guarantee. In either case, the other dimension is your hypothesis space is finite or infinite. So you have consistent and agnostic, and then you have finite and infinite. In each of these cases, we have an Occam's razor. We looked at the proof for these two things in some amount of detail. In both of these things, I just mentioned the bounds right now. With the infinite case, you have VC dimension. In the finite case, you have the size of the hypothesis space. This theory of pack learning has been in existence for 41 years now. And there have been extensions of this idea that exists, in particular when you know something about the data of the data distribution, or when you know something about the kind of noise, when you have a little bit more information. One important extension, if you want to follow up on this, or if this kind of stuff excites you, I would encourage you to look up something called pack-based theory. It's a pretty neat extension that makes some assumptions about prior distributions over the kinds of functions that should exist in nature. There are tutorials for pack-based that are available online. If you're interested, send me a message, I can point you to that. We've looked at a lot of computational learning theory in the last 2 weeks. And then we have things like GPT-4. How does this apply to that? Let me show you a figure from the GPT-4 technical report. I don't know why the images are terrible, but I will try to zoom in anyway. In statistical learning, okay, first of all, the idea is, wow, you can count the number of pixels there. So the thing is, computational learning theory is far, far from a complete theory of learning. Standard computational learning theory says, if you really want to make your classifier or your models work on real life data and work very well, then you need to think about VC dimension. You need to think about something called structural risk minimization, which we'll talk about later. We need to think about your loss functions and kind of adapt them, involving in ways to prevent overfitting and such things. And your generalization error goes down. In contrast, with large neural networks, there's really not much going on. We will talk about them later, but the empirical observations of modern machine learning completely ignore the lessons of learning theory. Not completely. Turns out that a lot of the ideas are built from the lessons of learning theory, but they explicitly do things that you should not be doing with learning theory lessons, and yet things work. Now, there are 2 ways of going about that. Well, there are 3 ways of going about that. First, you can draw some weird memes and put them in a tech report. But more importantly, you can kind of ignore all the theory and move on. But I think the more interesting way to think about it is this shows that the field of machine learning is in a very interesting and unique place where empirical practice has moved far, far ahead of theory. That means those of you who like theory, here's a fantastic challenge. Tell me why GPT-4 works. Prove a theorem about it. I have no idea how to, but if you do, you'll get rich and famous. No, you'll get famous, you won't get rich. Nobody gets rich with theory. Um, so it's an open challenge. This is an open challenge for anyone, and the field requires fresh ideas. But then why do we need computational learning theory at all? Computational learning theory was the first account of a rather important question of what does it mean to learn in a formal way. We use words like learning and memorization and such things in a loose way when we talk about people. That was the kind of vocabulary that was used with programs before learning theory came along. Computational learning theory frames the questions in a formal way. It talks about the key complexity parameters that are relevant for learnability, such as the complexity of the function class, the amount of data, the difficulty of the concept, and so on. That's one important reason why learning theory is worth knowing. We looked at mistake bounds earlier in the semester. It turns out that if a certain concept class is learnable under the mistake bound model, it means that the concept class is also learnable under the PAC model. So mistake bound learnability implies PAC learnability. And there are these standard, what are called online to batch conversion techniques that allow for that. The other interesting thing that any good theory does, and learning theory definitely did, was it raises theoretical challenges, and the answers to those theoretical challenges gave rise to entire new ways to think about learning. And it gave rise to learning algorithms and families of learning algorithms. In this semester, later after the break, we'll be looking at two of those questions. One of them is this rather intriguing idea. If I'm able to prove to you that a certain concept class is weakly learnable, for whatever that means, you can think of it as a certain concept class allows you have a learner, an algorithm that always gives you something that is slightly better than chance, a classifier that's just slightly better than chance. It's not as bad as tossing a coin, but it's not fantastic either. If your concept class is weakly learnable, can I somehow boost its performance to make it arbitrarily good? That's a question, right? It's a reasonable question. If something is only weakly learnable, if you can do better than chance on something, can you do arbitrarily well on that concept class? And the answer to that was yes. And it's a very cool learning algorithm called AdaBoost that answers that question. Another thing that comes out of this is we just saw this rather ugly looking expression that said the generalization error is going to be bounded by training error plus something involving the VC dimension. So my goal is to make the generalization error small. So can I define a training objective that involves making this thing small? If I make the thing inside the box small, my true error is going to become small as well. The answer to the first question gives you an algorithm called boosting. The second question leads to a very rich literature in machine learning called risk minimization, which is even today, I think, one of the most dominant ways in which we train learning systems. A concrete example of that directly jumped out of learning theory was the support vector machine. And we'll be looking at all these things after the break. Okay, any questions? That's the end of our lecture on learning theory. I see there was a... Any questions? Yes. Up to here. I don't want to post the video for the discussion because, oh, that's something I wanted to mention. I did not want to post the video for the discussion because I'm afraid that it might prevent people from asking questions. Sometimes people don't like asking questions if it means that it's going to be captured on YouTube forever. So everything till here is fine. After that, no. That doesn't mean that you shouldn't ask questions, because you should always ask questions. Because if you have a question, I guarantee 20 to 30 others have the same question. You're doing your friends a service. Yes.